Greetings, science family. We are going to be going over our Quiz 1 review. The main goal in mind, of course, is to just be prepared for the quiz and have a general understanding of everything that's going on. So let's start first by going over the different particles that are given off and what we call a radiation. So that energy. So the alpha particle, what is the symbol for it? Remember, all alpha particles always have a 4/2. Now you can write that as the alpha symbol, or you could write that as 4/2, don't forget, with the helium symbol. Remember, an alpha particle really is just a helium nucleus. It has 2 protons, 2 neutrons, it's positively charged. But when it shoots off of a nucleus, when it breaks down, that has energy, and therefore we call that radioactivity. All right, the beta particle, remember it has 2 ways to write it as well. It's always 0/-1. And you can write an E for electron or 0/-1 with the beta symbol. Remember, the beta symbol is just a B with a tail on it. By the way, a beta particle is stronger than an alpha particle, and it's considered basically an electron. The neutron has no proton, that's why it's a 0 at the bottom, but a 1 on top for the mass number, and it's an N. And then a positron is basically a positive electron, so it has no mass. We put a +1, think of it like a +1 charge, but that's not really what it stands for, but it's a little deeper than that. We'll just take it for that. But that's an E. It's like a beta particle, but with a positive charge. All right, so number 4 says, what is the difference between a nuclear bombardment reaction and a nuclear decay? So bombardment, the particles are smashing together, right? So they're smashing together. And then if you think about it, what is the difference? What is a decay? A nuclear decay means it's breaking down, breaking apart. So the reason we have nuclear bombardment, one we've learned about, is fission, right? The idea that we smash a neutron into a uranium-235 atom, and that starts the fission reaction. That would be a nuclear bombardment. Remember, in a nuclear bombardment, there's 2 things that come before the arrow. For nuclear decay, we know that that's the natural breaking down of a radioisotope to give off energy. And that means that, remember, for decay, we just start with 1 thing to the left of the arrow because you start with 1 and it breaks down into pieces. All right, let's zoom in a little bit and take a look at number 5 and 6. Got a little bit of a word problem here. If we take a look at number 5, write the nuclear equation for the beta decay of 230/91 Pa. So if protactinium, that's Pa, is going through decay, it's going to start all alone by itself to the left of the arrow. Why? Because it's going to start as 1 and it's going to decay, so it's going to break down. Now, since this is beta decay, that means it has to give off a beta particle. So 0/-1 is how we write that beta particle. But if you notice, that's not going to balance everything out, the numbers on top and bottom. So there must be one other thing that's given off. So if we start balancing that, remember that on the left side of the arrow is 230. Remember, the arrow is almost like an equal sign. So what plus 0 gives you 230? It's going to be 230. Now on the left side of the arrow, on the bottom numbers is 91. So on the right side of the arrow, what plus a -1 gives me 91? That's 92. And element 92, if you look on the periodic table, is uranium. So this beta decay actually gave off a beta particle and converted this element into a new one, which is uranium. Let's jump to number 6. Number 6, write the nuclear equation for alpha decay of promethium, which is 165/61. Okay. So if it's going to go through decay, that means this object is going to start by itself, all alone, and then after the arrow, it's going to break apart. It's going to break apart into 2 things. Alpha decay means that it's going to break apart into an alpha particle. We know alpha particles are 4/2 alpha, or you could write that as 4/2 He, but that's not going to balance out, so we must need something else. So we can use our numbers to figure it out. All right, 165 is on the left side of the arrow. Remember, the arrow is like an equal sign. So 4 plus what gives me 165? That would be 161. On the bottom number, it's 61. So on the right side, 2 plus what gives me 61? That's going to be element 59. Now, if I look on the periodic table, I find that the element is PR. And PR is called praseodymium, but it is now balanced. So this thing broke down into two things, an alpha particle and a new element, which is praseodymium. So let's zoom out a little bit and look into question number 7. How are alpha, beta, and gamma radiation different from each other when looking at penetrating power strength? So who's the weakest? Well, of all of them, alpha's the weakest. Who's a little bit stronger? The beta particle. And who's the strongest? It's going to be the gamma rays. So alpha's the weakest type of radiation and gamma radiation is the strongest. Remember, gamma needs like thick sheets of lead to stop it, where alpha particles, just like a shirt sleeve, will stop it. No big deal. For number 8, where are fission reactions used and found? All right, well, fission reactions can be used in what? Something that gives us electricity, our nuclear power plant, correct? And then also, where can fission use, which is the splitting of the atom? It can be used, unfortunately, in atomic bombs. If you ever read the book called just Uranium, though, it's pretty cool. A natural uranium fission reactor happened in nature somewhere in Africa. I think it's called like Sinkalobwe or Shinkalobwe. Forgive me on my pronunciation, but it's pretty cool to think of billions of years ago. There was actually like a natural uranium fission reactor happening in the ground. Pretty cool, they found it. All right, let's look at number 9. Define fusion in your own words. So for me, I would say, take the nucleus of two elements and what are we going to do with those nuclei? I'm going to say, and smush them together. Is smush a proper scientific term? No. But that's what's happening, right? The idea here is that you take two hydrogen nuclei, put them under such hot and high pressure environment that they actually fuse or smush together to create a larger element. And it gives off tons of energy when it does that, right? All right, what number am I on? Number 10. In a fission reaction, what is converted to pure energy? Pure energy, remember, during a fission reaction, if you put it all back together after it happened, there would be some mass missing. So remember, some of the mass disappears during the fission reaction. And remember, we convert that mass into pure energy because of the equation E equals mc squared. Remember, that little bit of mass turns into a lot of energy because that little bit of mass is multiplied by that huge speed of light squared. For number 11, describe how a nuclear power plant creates electricity. All right, instead of me writing this all out by my finger and going through it, I'm going to dictate, and then you can write down in your own words if you're having some trouble. So first of all, a nuclear power plant needs fission, right? So I'll do bullet points. From the fission, what's going to happen? Well, there's going to create a lot of energy and heat, and eventually we're going to boil water. When we boil water, what is boiled water? It's steam, right? So that steam that becomes high pressured is going to turn a turbine, right? So the next phase is that high pressure steam turns the turbine. And what's that turbine connected to? A generator. That generator is then going to spin and create electricity. Now remember, that high pressured steam needs to cool down. And remember that high pressure water in the fission reactor needs to cool down as well to keep the core safe and at a good temperature. But this is in a nutshell, pretty quick, how a nuclear power plant works. Split that atom, make that heat, boil that water, create high pressure steam. That steam is going to blow on and turn a turbine, which is going to spin it, which is going to spin the generator. The generator makes electricity. All right? How about for our next question? Let's see, what question number are we on? Number 17. Is all radiation dangerous? My friends, we should know that by now. No, not all radiation is dangerous. Why or why not? Listen up, I'm not going to write it, but you can write it your own way. It's because all types of radiation have different levels of energy. They have different types of penetrating power. Some of them have ionizing ability where they can strip electrons from the cells in our body, and some can't do that. So not all radiation is dangerous. We have to keep that in mind. Also, what's important is the dose, how much radiation we come in contact with. If it's a little bit, our body can repair. If it's a lot, it's harder to repair. So there's a lot of factors that go into radiation, whether or not it's dangerous. So just keep that in mind. Let's look at number 18. What is happening when an object is going through nuclear decay? When it's going through nuclear decay, we know that it's breaking down. When it's breaking down, what is happening? It's giving off energy, right? What do we call that energy during decay? We call that radiation. And what else? Besides breaking down, we're also creating new elements. So please, if you are going through this, do not just copy down word for word what I'm writing. Write down in your own words. This is not the entire answer. This is not a good enough answer. But explaining it, that energy we call radiation, we're creating new elements. It's breaking down from one object. So I'm just trying to go through it, but you need to do a good job of being concise and clear with your answers and answering it fully, not just copying the words I'm writing down. Let's look at number 19. Where is fission used in our lives? I think we kind of already asked that question, but we know that's a nuclear power plant. So I'm going to do nuclear P plant for short. Please, you write out the entire thing, nuclear power plant. And also atomic bombs, so for defense, right? I don't know if that's in our everyday lives, but I guess we are being protected daily by our wonderful service people. And where is fusion found in our lives? My friends, number one is the sun. Without the sun, we wouldn't exist. That's where we get all of our energy. So the sun is where fusion's happening. All stars run on fusion, right? And then don't forget, there are also hydrogen bombs, H bombs. Isn't a great thing? We also can call them a thermonuclear warhead. We can also call them a fusion bomb. For our next question, 21 on the docket here, what type of nuclear process is happening right here? We'll take a look. You're starting with a neutron. It's going to hit a uranium-235 atom, which quickly turns into uranium-236. It then looks like it splits apart into two elements and gives off 3 neutrons. My friends, we know what that is. That's the beautiful world of fission. If we look at question 22, though, what's going on? We've got something called deuterium and tritium. We never talked about that specifically. This is impossible. I must be just trying to make you fail and have you have no idea what's going on. Relax. Take a look at what's happening. These two things are coming together. By coming together, it looks like they created helium, a bigger element, but they also gave off energy and a neutron. What do we call when we put 2 nuclei together to create a larger element? Well, they fuse together. So we call that fusion, my friends. So don't panic when you see that. Use your common sense mentality. Kind of figure it out, what's going on. All right, let's look at 23. Ooh, these are great. Let's balance out our nuclear equations. Remember, an arrow is like an equal sign, so we compare this side of the arrow, the left side, to the right side. If we look at the left side, 14 plus 4 gives me 18. So 18 plus 0 gives me 18 on top. On the bottom, it's 7 plus 2 is 9. 8 plus 1 is 9. Ooh, what is 0? No mass, but has a 1 on the bottom. That's going to be a positron, my friends. And what's happening here? Is this decay or bombardment? Well, before the arrow are 2 things smashing into each other. So that is definitely a bombardment. Ooh, but a positron was formed, but look what was started and used in the very beginning. 4/2He is an alpha particle. Ooh, so we used an alpha particle, and take a look. That is definitely an alpha bombardment for a nuclear equation because the alpha particle starts off by hitting the nitrogen. All right, not bad. Let's take a look at the next step. We're starting with one object by itself, and it's going to break down into 2 pieces. Sounds like nuclear decay to me. All right, let's balance out both sides. On the left side, we've got 240 on top, so 236 plus 4 gives you 240. What's on the bottom? 95. So 93 plus 2 gives you that 95. 4/2. Oh, is that an element or particle we've learned about? Yeah. 2 protons is helium, or remember we could use the alpha symbol because 4/2 is the alpha particle. So what would we call this? It would be called alpha decay because the thing is breaking down, americium is breaking down into an alpha particle and something else. Take a look at the next one. You've got one object by itself breaking into 2 parts. That has to be decay. All right, let's balance it out. Remember the arrow's like an equal sign. On top you have 13. So 12 plus 1 gives you 13 on top. On the bottom is 7, so 7 plus 0 gives you 7. Ooh, what has a mass but it doesn't have an atomic number at the bottom? That's a neutron, right? So a neutron is being given off. So what would we call this? We could call this neutron decay. It's breaking down and giving off a neutron. Pretty cool. If I scroll up to 24 here, ooh, good. This is a word equation. I like these. Putting our knowledge to the test. We have an alpha bombardment of nitrogen-14, and only one new isotope is created. Ooh, so it looks like after the bombardment, only one thing is created. Fine. It says nitrogen-14 is bombarded by an alpha particle. So I'm going to write nitrogen-14. I'm also going to write an alpha particle. I know is 4/2 alpha, or He. All right, nitrogen, if I look on the periodic table, is element 7. So now I have this thing completed. Now, if it's alpha bombardment, the reason I put alpha plus nitrogen is because before the arrow, they have to be added together because they're smashing together. Now, if I want to solve for this, it said that only one isotope is created. So now I know that there's only one blank space to the right. Well, 14 plus 4 is 18, and 7 plus 2 is 9. So that's going to give me 9. Well, 18 over 9 must be some type of element because it's not a small like particle. So element 9 on the periodic table is F, fluorine. So look at that. Nitrogen, when it gets smashed with an alpha particle, becomes fluorine in this case. Pretty cool. We're creating new elements. Remember, old chemists were trying to do that years ago, like turn lead into gold, and then they thought it was impossible. Alchemists were doing that. Problem was, we didn't know about radiation yet, that actually some elements naturally turn into other ones when radioactivity happens, which is pretty cool discovery. All right. Number 25, let's finish strong. Aluminum-27 is bombarded with a neutron. Okay, so aluminum is going to be bombarded with a neutron, so it's going to be hit by a neutron. It says it then is going to create to me is like an arrow, an alpha particle, and one new isotope. So it looks like an alpha particle is going to be created and one new thing. Now that I have the skeleton outline, I'm going to start plugging in some info. It says aluminum-27 in the words, so that must be the mass number. I know aluminum on the periodic table, if I check, is element 13. Neutron always has the same notation, 1/0. It has a mass, but no protons. It creates an alpha particle, it says. So I know alpha particles are always 4/2. Remember, I don't have to write that alpha symbol. I could write He as well for helium. And now that I have that, I can fill in my blank spot. How so, Mr. J? Well, just use my math. 27 plus 1, which is on the left side of the arrow. Remember, the arrow's like an equal sign. 27 plus 1 gives me 28. So 24 plus 4 gives me 28. That's how I figure out my top number that's missing. On the bottom is 13 plus 0, total of 13. So 11 plus 2 should give me 13. And the element 11 on the periodic table is sodium. So I balanced it out. All right, science fam, it looks like we cruised through our quiz review, but a lot of main ideas: fission, fusion, nuclear equations, radiation, and what are those particles? Alpha, beta, gamma, positrons, neutrons. We also talked about the mass number on top, atomic number on the bottom, making sure they balance out, the difference between decay and bombardment, and of course the use of fission and fusion in our everyday lives. Hopefully this has been a great review for you. And from there, anything you struggled with or that you really needed this video to get through, that's what you should be studying for your next quiz. By focusing on what we're weak with and asking deeper questions, that's what's going to better prepare us. All right, science fam, thanks for hanging in there. Take care. Be well.